In this module, we will be introducing the simplex algorithm. The simplex algorithm is the most important algorithm to solve linear programming problems. Let us look at the summary of the graphical and algebraic methods with which we ended the previous class. We have seen the graphical and algebraic methods in the previous module, and we understand that the graphical method is useful when we have two variables. The algebraic method can be used when we have more than two variables or large number of variables, but it evaluates a large number of solutions. There are times it evaluates infeasible solutions also, and we do not have a way to understand a priori that this solution is going to be infeasible. So, we have to evaluate it and then understand that it is infeasible. So, in some ways there are three aspects of the algebraic method which, if we can correct using a better algorithm, we can solve linear programming faster and better. Now, the algebraic method evaluates infeasible solutions. So, is there a way to eliminate infeasible solutions? Secondly, is there a way to evaluate better solutions as we move along? And the third is there a way we understand that we have reached the best solution and we do not have to evaluate any more? So, these three questions remain at the end of the algebraic method. Let us go back to the same example. In the algebraic method, we evaluated 6 solutions and we did not have a way to know that our solutions 3 and 4 are going to be infeasible before we evaluated them. Now, is there a way not to evaluate them at all and evaluate only the remaining 4 basic feasible corner points is the first question. Second observation is, if we look at the 4 corner points, we seem to have evaluated them in the order where the solution gets better and better. Now, let us assume that we had evaluated number 5 and we have a solution with 63, and let us assume that we have not evaluated the second solution. Now, is there a way not to evaluate the second solution, because even if we evaluated the second solution, we are going to have 60 as the objective function value, and since we are maximizing the objective function, there will not be a way by which solution number 2 can be optimum if we know that there is a solution with 63. So, it so happened here that we evaluated better and better solutions, but can we make it a distinct part of the algorithm? We have not made it a part of the algorithm. Can we make it a part of the algorithm? Now, instead of evaluating the 6th solution last, if we had evaluated as a 4th or 5th solution, is there a way to understand at that point that I have reached the optimum and I do not have to evaluate any more? So, these 3 issues we try to address in an algebraic way, and later we extend that to what is called the simplex algorithm. So, let us go back to the same example where we have added the slack variables. There are 2 slack variables, x3 and x4. They do not contribute to the objective function. They also are greater than or equal to 0. Now, let us assume that we want to start the algebraic method in a certain way. Because there are 2 equations and 4 variables, we can only solve for 2 variables at a time, and those 2 variables we are going to solve are called basic variables. It also means that the remaining 2 variables have to be fixed, and they are fixed to 0. They are the non-basic variables. So, by simply looking at these 2 equations, a very easy way to start is by treating x3 and x4 as basic variables, which means x1 and x2 are non-basic variables and they have value 0. So, we start with x3 and x4 as basic variables, and we write the equations in such a way that they are written as basic variables in terms of the non-basic variables. The first equation is 3x1 plus 3x2 equal to 21. Now, from this equation we are writing x3 is equal to 21 minus 3x1 minus 3x2. Now, x3 is your basic variable, x3 is a basic variable. Now, the second equation is 4x1 plus 3x2 plus x4 equal to 24. This is written as x4 is equal to 24 minus 4x1 minus 3x2. So, x4 is your basic variable. The objective function is 10x1 plus 9x2 or 0 plus 10x1 plus 9x2. The 0 comes because x3 and x4 do not contribute to the objective function. Now, from these two equations where we have written the basic variable in terms of the non-basic variable, the non-basic variables take value 0, therefore, the solution is x3 equal to 21, x4 equal to 24, which is one of the basic feasible solutions that we got through the algebraic method. So, we have the starting solution x3 equal to 21, x4 equal to 24, x1 x2 equal to 0 is basic feasible because it satisfies the non-negativity restriction. It also satisfies the two given equations. So, now we have written the basic variables in terms of the non-basic variables. Now, x3 equal to 21, x4 equal to 24 would give a contribution of 0 to the objective function plus 10x1 plus 9x2. We still write 10x1 plus 9x2, x1 and x2 are right now at 0. Now, we have a solution with x1 equal to 0, x2 equal to 0 and z equal to 0. Now, the objective function has a value 0 and we wish to maximize the objective function. Now, this z, which is the objective function, can be increased if we increase x1 or we increase x2. Both x1 and x2 are at 0. So, if we increase x1, the rate of increase is 10, and if we increase x2, the rate of increase is 9. So, we start with increasing x1 because it has a larger rate of increasing the objective function. So, we increase x1. So, when we increase x1, we call it by saying we enter x1. Now, as we increase x1, let us say x1 is at 0. Now, if we make x1 equal to 1, then x3 will become 18 from 21. x4 will become 20 from 24. If we increase x1 to 2, then x3 will become 15 and x4 will become 16. As x1 increases, x3 and x4 start reducing because of the negative sign. And as we keep increasing x1, one of them will quickly first become 0. So, this for x3 to become 0, we have to increase x1 to 7. For x4 to become 0, we have to increase x1 to 6. So, as we keep increasing x1, when x1 reaches 6, x4 becomes 0 first. And if we increase x1 further, x4 will become negative, which we do not want. Therefore, we say that x1 can be increased up to 6. So, x1 is increased up to 6 and x1 is now going to become basic because it is not having a value 0. x4, which was 24, now becomes 0 and will become non-basic. Therefore, we write the equation with x1 as a basic variable and x4 as a non-basic variable. So, this equation is now rewritten as this equation, which gave us x1 equal to 6, is now rewritten as 4x1 is equal to 24 minus 3x2 minus x4. and this is simplified and again written as x1 is equal to 24 by 4 6 minus 3 by 4 x2 minus 1 by 4 x4. So, now x1 becomes basic with value equal to 6. Now, we have to find out the value of x3, and we do that by substituting for x1 in the first equation or in the equation for x3. So, we now use this value of x1 that we have taken and we substitute it in this x3 equation to get x3 is equal to 21 minus 3 times x1, x1 has been recently written, minus 3x2. So, when we do this simplification, we will get x3 is equal to 3 minus 3 by 4 x2 plus 3 by 4 x4. 21 minus 18 will give that 3. We have plus 9 by 4 x2 minus 3 x2. So, minus 3 x2 is minus 12 by 4. So, we have minus 3 by 4 x2, and then we have plus 3 by 4 x4 from this equation. And then we now write the objective function as, it was originally 0 plus 10x1 plus 9x2. So, the objective function becomes 0 plus 10 times x1, x1 is 6 minus 3 by 4 x2 minus 1 by 4 x4. So, 10 times 6 minus 3 by 4 x2 minus 1 by 4 x4 plus 9 x2. So, 10 into 6 60 minus 30 by 4 plus 9 minus 30 by 4 plus 36 by 4 is plus 6 by 4, which is 3 by 2 x2, and 10 minus 10 by 4 is minus 5 by 2 x4. So, from this solution, the first solution, we have now moved to another solution that we have written here. Now, this second solution has x1 equal to 6 and x3 equal to 3, and the objective function value is equal to 60. 10 into 6 is 60. So, we have moved to another solution right now. Now, again we wish to maximize the objective function. The objective function is now 60 plus 3 by 2 x2 minus 5 by 2 x4. x2 and x4 are non-basic, so both of them are at 0, and therefore, the value of the objective function is 60. Now, z can be increased further if we increase x2, because x2 now has a positive rate of increasing z. The coefficient is positive, so it has a positive rate of increasing z. Now, by increasing x4, we cannot increase z, we actually end up decreasing z because of the negative coefficient. Because it has a negative coefficient, the only way by which we can increase z through x4 is by decreasing x4, because x4 is at 0. But if we decrease x4, x4 will become negative, which will violate the non-negativity restriction, which is here. Therefore, we do not consider x4 as a way to increase z. We look at only x2 as a way to increase z, and since x2 has a positive coefficient, it is at 0. So, if we increase it, we can further increase z or increase the objective function. Now, we see the extent to which we can increase this x2. Now, as x2 increases from this equation, you realize that x1 is going to reduce. As x2, for example, if x2 becomes 1, then x1 will become 6 minus 3 by 4. So, it reduces. So, this equation would allow x2 to increase up to 6 into 4 divided by 3, it would allow x2 to go up to 8. It would allow x2 to go up to this 8. Again repeating, 6 and 3 by 4. So, the best value that x2 can take till x1 becomes 0 is 6 into 4 by 3, which is 8. At x2 equal to 8, 3 by 4 x2 will become 6 and x1 will become 0. This equation we have to look at this. So, this becomes 3 as x2 increases, as x2 becomes 1, this will become 3 minus 3 by 4 and so on. This would allow x2 to go up to 12 by 3, 4. So, we have x2 going up to 4. So, now as x2 becomes 4, this equation will make x3 come to 0 first, and therefore, the limiting value is the smaller of the two values. So, we will now say that x2 will replace x3 from this equation, because this equation allows x2 to go up to 4, which is here, So, this is the equation that we will be using, particularly this equation, which we will be using. Now, x2 will come to the left hand side of this equation, x3 will become 0 and go to the right hand side of this equation. So, from the previous solution, x3 was 3 minus 3 by 4 x2 plus 3 by 4 x4, x2 comes to the left hand side and x3 comes to the right hand side. Now, this is written as 3 by 4 x2 is equal to 3 minus x3 plus 3 by 4 x4, and x2 is written as 4 minus 4 by 3 x3 plus x4. From this, you multiply everything by 4 by 3, you get this expression. Now, go back to the previous one and rewrite x1 in terms of x2. So, x1 is 6 minus 3 by 4 x2 minus 1 by 4 x4. So, we substitute for x2 from this equation, we substitute for x2 into x1 and we get 3 plus x3 minus x4. Now, once again we go back and write the objective function now. The objective function was 60 plus 3 by 2 x2 minus 5 by 2 x4. So, we go back and substitute for x2 from this equation into the objective function and rewrite it and simplify it to get 66 minus 2 x3 minus x4. So, we now have another solution, which is x2 equal to 4, x1 equal to 3 and objective function equal to 66. x3 and x4 are non-basic, they are at 0. Now, we wish to maximize z further and we realize that z can be increased beyond 66 only if we decrease x3 and x4, because both have negative coefficients. And if we decrease them, they will become negative because they are at 0. So, we do not try to decrease x3 and x4. So, we do not have a variable which can now help us increase the value of the objective function. We now stop the algorithm by saying that we have reached the best solution, and the best solution is x1 equal to 3, x2 equal to 4 with z equal to 66. So, now we have shown or developed or used an algorithm which essentially does what we wanted to do. Now, this algorithm did not evaluate any infeasible solution. It evaluated 3 solutions, but it did not evaluate any infeasible solution. It evaluated only basic feasible solutions. It evaluated 3 out of the 4 basic feasible solutions, and it also gave solutions with better values. The objective function value was 0, 60 and 66. When it reached 66, it knew that it had reached the optimum. It did not evaluate the 4th one. So, this way this algorithm is able to meet our requirement of refining the algebraic method and making it better. This is the basis of what is called the simplex algorithm, and we will see the simplex algorithm in the form of a table in the next class.